Okay, so we're going to put it all together, things we've been working on to graph the rational functions. Okay, so here's kind of a nice straightforward rational function. Okay, so let's see. So what's the first thing we did? How do you look at end behavior? As long as it's the end and it's a rational function, like, oh, this function behaves like x squared over squared, which tells you that this limit is 1. And then that tells you that the graph has a horizontal asymptote of y equals 1. Okay, so we can tell that, excuse me, from looking at the function before we factor it. All right, let's grab a different color. And let's look at the next part. Okay, what if we factor? So we'll know that f of x is equal to, I think it's x minus 1, x minus 2, over x minus 1, x minus 4. And why is that important? We can see which values of x are not in the domain. Which numbers can we not input and get an output? So we know that x can't be 1 and x can't be 4. Okay. All right, now let's see. Now if we reduce the function, we know it essentially behaves like, and you can't always reduce them. I think this one, the x minus 1's reduce out, and that's like x minus 2 over x minus 4. So in the reduce function, the only thing that x can't be is 4. So why is this important? Because we've got these special numbers to think about. At x equals 1, you can't get an output for f, but you can get an output for the reduce function. That gives you removable discontinuity. So we'll do that one first. At x equals 1. How come? Because f of 1 doesn't exist. You want to look towards the language of calculus. But the limit as x approaches 1 of f of x would be, you could input 1 into the reduced function, 1 minus 2 over 1 minus 4, which is minus 1 over minus 3, which is a third. So you know you have a removable discontinuity at x equals 1. You think the function's going to go to 1/3, but there's just no point there. Okay, but that same thing doesn't happen. So at x equals 4, because the limit as x approaches 4, now you have to pick a direction. So how about we just pick from the right of f of x. And let's kind of make a little note on the side. If we put in 4 in the numerator, it would be 4 minus 2, and you're coming from the right, so 4 plus minus 4. This is 2. This is 0 plus. You're like, oh, that's going to explode up. So in calculus, when we start the year together in August, it's super important to be able to use limits to justify behaviors of functions. Okay, so that's kind of some things we've been working on for the last couple weeks. And here's what's new. We're going to make a sign chart. This is so helpful. You ready? And everything we're going to put in the sign chart is all the things that make the output of the function literally be 0 or make the output of the function be undefined. And so those were the numbers 1, 2, and 4. And you want to be careful to put them in increasing numerical order, just like on a number line. I don't really care about the spacing, but you care that they're in order. Okay, so let's see. We said at 1, we have a removable discontinuity. I like to make myself a little note. At 2, you actually get a 0 of the function. And at 4, you don't get an output, but you get a vertical asymptote. And there's those 3 points making 4 regions. Okay, so now we're going to go look at the reduce function. I'm going to make a template. Again, this is a Miss Brady thing. I'm not the only one that does that, but to me, this is the most straightforward way to organize it. I'm going to go back and look at my different factors. We'll do it by color so it'll be easier. Okay, so we're going to look at x minus 2. That makes 0 at 2. If we pick a number to the right, like 3 or 7, 7 minus 2 is a plus number. So everywhere to the right, that factor is positive. which means everywhere to the left that factor is negative. Okay? All right, let's get a different color. Let's do purple. Okay, now we're going to look at x minus 4. That is 0 here. If you pick a number bigger than 4, like a million minus 4 is a plus number, which means everywhere to the left, you've got negative. Okay, so why do we care about that? Because we are going to figure out in each region if the function's positive or negative. So negative over negative is plus, and this is plus, and this is negative, and this is plus. And in a second, what we're going to do is just organize all those details and graph the function.